OSPF. Your OSPF, first of all, it is an open standard protocol. Okay. Initially, your EIGRP was Cisco proprietary. Okay. So EIGRP was not supported in the other vendor devices. Like if other than Cisco routers and other devices, EIGRP was not supported. But later on, Cisco declared it as open standard. So now your EIGRP is also open standard. Okay. But till then, other vendors were going with the OSPF. Okay. Then your OSPF uses the Dijkstra's algorithm. Dijkstra's SPF, shortest path first algorithm. Shortest path first. This is the algorithm that your OSPF uses, and because of these two things only, your OSPF has the name open shortest path first OSPF. Okay, because it is an open standard protocol and uses Dijkstra's SPF algorithm, so it became OSPF open shortest path first. Okay, so the full form of OSPF is open shortest path first, and it is a link state protocol. It is a link state protocol. EIGRP protocol number is what? 88. Here the protocol number is 89. AD value of your OSPF 110. Okay. Then your OSPF uses two multicast addresses. Your RIP version 2. If we discuss RIP version 2 was using 224.009. Your EIGRP was using 224.0010. Your OSPF is going to use 224.005 as well as 224.006. Okay. 224.005, it will use whenever the traffic is going for all the OSPF routers. When the traffic is destined for all the routers, it will use the destination address as 224.005. And if the traffic is going for DR and BDR, these are two special type of designation in your OSPF. Okay. So if the traffic is going for DR and BDR only, it will use the address 224.006. Right now, do not get confused with the DR BDR. We'll discuss what is DR BDR, how DR BDR are elected, and how this traffic is using this 224.005 and 006. Everything we'll see practically. Okay. Works on Dijkstra's algorithm, or sometimes in short, you'll also call it as a SPF algorithm. Okay. Then in your, if you discuss in your EIGRP, we were using the concept of autonomous system. Correct. But in OSPF, what happens? We use the concept of areas. Okay. What is an area? An area is a subset of an autonomous system. Okay. Like this is one big autonomous system, means one big company that is handling lots of routers. Let's say 100 routers they are handling. R1, R2, R3, like that they have router 100. Lots of routers they are handling. Now, if there is a change on this router, there is a change, let's say a network is added or a network is removed and interface is down, anything. If there is a change on this router will inform everyone. So the information will pass from here to here, then here to here, then here to here. Like this, it will reach router 100. Right? So it will take up some time. It is going to take some time. So for faster convergence, so that the information can be delivered fastly, what your OSPF does, your OSPF breaks this one single autonomous system, one big autonomous system into multiple areas. In your OSPF, we break the one single autonomous system into multiple areas. Okay. Now what will happen? Let's say this is one area, this is another area. These are like two areas. Okay. Now some routers will be in the first area and some routers will be in the second area. Okay. Like that. These routers will be connected to each other and these routers will be connected to each other. Correct. Now what will happen? These routers, let's say this is area, for example, 0. This is area 1. These are the two areas. Now the routers in the area 0, they will have information about area 0 only. Means not just as a concept understand, but actually in the area 0, you will have information about everything. Okay. So right now let's consider them as a area 1 and area 2. Okay, so the routers in this particular area will have the information about this particular area only, means what all the routes are there in this area. Similarly, the routers in the area 1, they will have information about area 1 only. Okay, they will not care about the changes in the area 2. Okay, but again, these still belong to the what? Same autonomous system, means they should communicate. So if you want communication between two different areas, there will be one special router where both the areas will be configured. Okay, where both the areas will be configured. Okay, so this router will be providing communication between the different areas. Okay, is that clear? And the router that is having its interfaces in multiple areas, okay, that will be known as ABR, area border router. But specifically in case of Cisco, there is a condition for ABR. What is the condition? An ABR should have one of its interface in area 0. In case of Cisco, this is a requirement that if a router has to be known as ABR, it should have one of its interface in area 0. See, whenever we are discussing the area concept, in case of OSPF, area 0 has a very special significance. Okay, what is the significance? Your area 0 is known as the backbone area. It is known as the backbone area. Now, why it is known as the backbone area? Because all the traffic, if these two areas, area 1 and area 2, they want to communicate, then they have to be connected to area 0. Okay, this is, you can also say, the transit area. Without this transit area, two areas cannot communicate. Without this transit area, two areas cannot communicate. Okay, so that's why there is a requirement that if a router has to be called an ABR, it should have one of its interface in area 0. Okay, in case of Cisco, this is the requirement. If you search ABR on the internet, mostly you will find what? That, okay, any router that is having its interfaces in more than one area, or that is allowing communication between two areas, that is the ABR. No, that is with the different vendors and the internet. But according to Cisco, if you go, then an ABR should have an interface in the area 0. That is mandatory. Okay, this is clear. So area is nothing but a subset of an autonomous system. Means a large autonomous system in case of OSPF that is divided into smaller parts, and those smaller parts are known as areas. Okay, now why the autonomous system has been divided into the areas? For faster conversions. Okay, what does it mean with the faster conversions? Means if there is any information, that will be shared faster. The updates will be sent faster. Okay, all the routers will come to know faster. See, there was a time when R1 was giving the information from R1 was reaching R100. That was taking time. But now in this, let's say you have only R1 till R50. Obviously, it is going to take less time, right? So like this, there will be faster conversions in case of OSPF. Is that clear? Means if there is any change, the change will be updated fastly in the topology. Clear? Then there we were using autonomous system number. Here we will use the process ID. Now this process ID, this is local to the router. Okay. On different routers, you can have different process IDs. Okay. Like on router 1, you can have one process ID 1. On router 2, you can have process ID 2. And still they will communicate. It is not like EIGRP that the autonomous system number has to be same on all the routers. No, not a requirement. Okay. Then OSPF uses DR-BDR concept. This we will discuss. And OSPF is classless protocol. Classless means it is going to support your VLSM and CIDR. This is clear? And yes.
If in area 2, one link goes down, then do it something pass to area 1 or
yes, we have ABR. We have one special router, right? ABR that will be communicating, providing communication between two areas, but it should be connected. See, these two areas, if there is no area 0, they will not even communicate. The information will not pass. Okay. If these are two different areas, let's say area 1 and area 2, by default, they will not communicate, even if you have this router connecting the two areas. Okay, by default, they will not communicate. They will only communicate if they are connected to area 0. Two areas will never communicate until or unless they are connected to the area 0, either physically or virtually. Okay, when you will go to your CCNP, you will read the concept about, let's say, if we have a situation like, okay, we have a situation in this side, we have area 0, area 1. Okay, then we have area 2, like that. Now what will happen? Area 0 and area 1 will communicate, but area 1 and area 2 will not communicate. Let's say you have some routers here, like this. Now what will happen? Area 0 and area 2 will communicate, but area 1 and area 2 will not communicate. Why? Because area 2 is not directly connected to area 0 or not virtually connected to area 0. So area 1 and area 2 will not have the communication. So in that case, you will read a concept about virtual link. So what you will do, you will be creating a virtual link like this. Okay, means not a physical cable, but you will be writing one extra command for creating the virtual link. And then these will able to communicate. Otherwise, they will not communicate. Either you will have to take a cable from here and then connect, then they will communicate, or else they will not communicate. Is that clear? Yes.
That will communicate.
No, by default, they will not communicate. If you do not have virtual link, area 0 will communicate with area 1, no problem. But area 1 will not communicate with area 2. This communication will not be there by default. Why? Because your area 2 is not coming.
Area 0 with area 2.
No.
That also
No.
Two communications will not happen.
No, that will not happen. These two communications will not happen.
Be area 0 and area 1.
Only area 0 and area 1 will communicate by default. Why? Because area 1 is directly connected to area 0. Okay. So you will be creating a virtual link there. Okay. So this concept is again part of your CCNP. Right now, you do not need to worry. Yes.
Sir, in fast topology,
Hmm.
if fast router, if something happening in fast router, if the information plotted out everywhere,
Hmm.
one by one, and in area 2 and area 1, it also plot the information to area 1 and area 2 everywhere. So
Yes,
what is the
but-
difference?
Yes.
So what is the difference of area?
Which one you did not understand?
Means fast topology. If
Hmm.
R1
This one?
fast topology R1 to R100.
Okay, R1 to R. Okay, this one. Yes.
If one link goes down on
Hmm.
R1,
Hmm.
the information will send to R2, R3 like this to
Hmm.
R100.
Correct.
In area in area 2 and area 1 topology, if area 2 one router link goes down,
Hmm.
the information will plot to the area 1 like to 1 to 100.
Okay.
So what is the difference between area?
First difference will be, see, these routers are considerate about this particular area only. Okay. So the information will travel faster between R1 and R50, right? So they will update faster. And now the remaining task is for this router who is connecting, let's say ABR. This will deliver the information. So now how much time it is taking this side, not worry. So first thing. Second thing, again, we still have to read DR, BDR concept. Okay, because on each and every Ethernet segment, your DR and BDR will be generated. Okay, now what happens whenever there is a change, instead of telling every router, it will tell only the DR, and DR will deliver the information. Okay, so still lots of concepts are there, don't worry. Okay, is that clear? Okay.
Sorry.
Yes,
If ABR goes down
ABR goes
from
down.
area 1, what will happen? Sir?
See, ABR is nothing, a special router, like say this router is having two interfaces. So this side interface we will configure in area 1, this side configure
Area 0.
area 0.
And
Yes.
from area 1 side it will go down.
Okay, this interface goes down.
Communicates.
How it will communicate? No interface.
Then what would idea time what should we do?
Then no communication. You have to troubleshoot, or else you provide redundant links. Okay, that are only the option. Yes, Vincent.
In between the areas, there is only virtual links. There is no physical link. So they will be communicating each other.
Sorry.
In between the areas, there is only virtual links. There is no physical links.
Okay. Let's say I'll add one more area here.
Yeah.
Okay.
In between area, there is only virtual link. There is no physical links connecting.
Correct.
So they will be passing the information to each other.
Yes, they will be passing. How? See, the information will still pass through these links only. Okay, this is just a concept of connecting them virtually using the virtual link. Okay, means basically allowing the flow of communication between different areas. Okay, and this is why, see, because in case of Cisco, we have like ABR is what, who should have one interface in the area 0, first thing. Second thing, all the areas, if they want to communicate, they have to connect to the area 0. So that's why your area 0 is having higher significance here. Okay, and that's why it is known as backbone area, because without a backbone area, two areas will not be able to communicate. Is that clear?
Okay.
Okay.
Also between two areas, the area border will be there.
Yes. See, if I'm saying between area 1 and area 2, I will have an area, but they will not communicate until or unless I connect it physically or virtually to the area 0. So again, in case of ABR, area 0 will always be there. Okay, so that's why your Cisco says that your ABR should have one of its interface in the area 0. Okay, is that clear? Then in case of OSPF, we have 7 neighboring states. They become neighbors. Okay, let me do one thing. Let me first show you the basic configuration, and then we'll come to the neighboring states.
It's like these 3 points, like between two areas, there should be ABR with one point. And ABR interface should be.
ABR should have one of its interface in the area 0.
Area 0.
Yes.
And all areas should be connected to area 0.
Yes, if they want to communicate. Okay. .0/24. Same topology I'll create like yesterday only. Okay. The IPs are all ones. So 192.168, 12.1. And here it will be 12.2. Configuration terminal. And this is for R1. Interface V0/0. IP address. R2. interface loopback 1. Loopback 2, 20, loopback 3, 30. Done. See, Notepad will make your configuration real easy. And this same configurations you can use in the real routers also. Okay. In the physical also, you can create configurations in your Notepad and you can use them. Paste. Show IP interface. Okay, all IPs are set. Pin 192.168.12.1. Okay, everything is correct. Now we just have to go and configure what? OSPF. So again, similar configuration is there. Okay. You have to say router OSPF. Okay, and which networks you will give. So for that, do show IP route. And all the routes with the C code you have to give. All the networks with the C code you have to define. So only one. So we will say router OSPF, and let's say this is router 1, so I will use the process ID 1. Okay. If you see the range of process ID, it is same like your autonomous system number. Router OSPF, check 1 till 65,535. So let's say on router 1, I'm using the process ID 1. Then we have to define the network. So I will say network. Which network is directly connected here? 12.0. 192.168.12.0. Okay, now in case of EIGRP and RIP, we just directly hit enter. But here you have to give one extra thing that is known as wildcard mask. Okay, now what is wildcard? We know subnet mask, right?
Reverse of subnet mask.
Yes. We know what? Subnet mask. What is subnet mask? Let's say for /24, the subnet mask will be 255.255.255.0. For this subnet mask, you want to calculate wildcard mask. So if you want to calculate wildcard, all you have to do 255, subtract your subnet mask from 4 times 255. 255, 255, 255.255. And from this, subtract your subnet mask. So if I subtract my subnet mask, this is my subnet mask. What will be the wildcard? Exactly. Is that clear? This is how you will calculate. You have to subtract your subnet mask from 4 times 255. And you will get the wildcard mask. Okay. So here the wildcard will be 000.255. Okay. Then after that, you have to define the area also. So let's say here, as of now, we will consider that this entire network, let's say belongs to area 0. Okay. So what you have to do, you have to define here area also, that to which area it belongs. So I'll say which area? Area 0. Configuration is done. Now same configuration on R2. Do show IP route. So if I see here, 4, router OSPF in the router 1, we use process ID 1. Here I'll use 2. So that you can know that, okay, router IDs, they do not make any difference. Routers will still communicate. Okay. So router OSPF 1, and then you're going to say network. What is the wildcard for /24? 255, and they also belong to area 0. 20, 30, 192, 168, 12.0. Area 0. And now they will become the neighbors. Okay. You'll see. It will take up some time to become neighbors. And now you see they become the neighbors. Okay. They became what? Neighbors. And if you see, okay, yesterday I gave you a task, right? So why EIGRP is having the code D? Forgot. Dual algorithm. You wait. Yes. Not checked. See, I'll show you. Because before BGP, there was a protocol EGP. And for EGP, the E was already reserved. So to prevent confusion, they used D instead of E. Okay. See, on R1, we did not configure. So if I check do show IP route, do you see here? E is reserved for EGP. So that's why they went with the D. And now you see the code is what? Where is D? It's O, right? And O is for OSPF. What is the AD value? 110. This is what? This is known as metric. Okay. Metric is what? 2. Okay. Then these are the networks. Now you will be able to ping. Ping 10.1.1.2. Why I got the error? Do. 20, 30. Okay. We have the communication. This is clear. Basic configuration of OSPF. What did we configure?
So you can use same process ID on each router.
Yes, you can use same process ID also, different also. Doesn't make any difference. Okay. So you will say here router OSPF, and then you will give the process ID. Then you will say network ID. These are all the directly connected networks. Okay. Do not try to think, okay, the network you want to reach. Network ID, wildcard. Then after you'll say area, and you'll give the area ID. Okay. This is how you will configure the OSPF. This is clear.
Sir, excuse me, sir.
Yes.
So yesterday I was watching a video, they configured like this, OSPF, then network ID, network OSPF ID. Then they used, I forgot. This is what?
Router ID.
Yes, sir. Router
They
ID.
used router ID.
Router
The
ID.
concept is coming.
Then,
Yeah, after router OSPF, they,
OSPF, 1 area 0 something.
that is another way to enable OSPF on the interface level.
That works also.
Yeah. Okay, that works also. Done. That is a way of enabling OSPF on the interface. Okay. Yeah,
So what in real scenario, we will get first ID from lender. In the real scenario, we will get first ID from organization.
No,
Right.
that is random. You can configure anything.
Right.
Okay. This is clear, the basic configuration. Okay. Now let's come to the neighboring states. And before coming to the neighboring states, your OSPF is going to create 3 tables. Okay. Your OSPF as well as your AIGRP, both of them creates 3 tables. Okay. The first table is known as the neighbor table. The first table is known as the neighbor table. The second table is known as, in case of OSPF, it will be known as OSPF database. OSPF database. In case of AIGRP, it will be known as AIGRP topology table. Okay. Then the third table is known as routing table. Okay. And your OSPF database, this is only the thing that is also known as LSDB. Link state database. Okay. Now, neighbor table is going to store the list of all the neighboring routers. Okay. This is what? List of neighboring routers. OSPF database going to store the information about all the networks as well as their associated routers. Okay. Kind of, you can say, list of all networks. List of all networks with their routers, router IDs. Then routing table, your routing table is going to store the list of best routes. Is that clear? Okay. Now, always, first of all, your neighbor table is created. First of all, your neighbor table is created. Then once neighbor table is created, the routers will exchange the information. They will create what? The database. Now the database is nothing but the raw information they are exchanging with each other. On this OSPF database, your Dijkstra's algorithm, the SPF algorithm will be run and the best paths will be calculated. And those best paths, they will be stored inside the routing table. So they are created in this order only. First of all, neighbor, then database, then routing table. Is that clear? Okay. Now, how they will become the neighbors? So for becoming the neighbors, they will use these packets. For creating all these tables, they will use these packets. Means these are the messages that are being exchanged in case of OSPF. Okay. And when they are becoming neighbor, they are going through these 7 neighboring states. Okay. Now we'll see one by one how these neighboring states are coming, as well as how these packets are getting exchanged. Okay. Let's consider this is your router 1. This is R1. This is R2. They are connected to each other and you configured OSPF on them. Okay. As soon as you configure OSPF, let's say first of all you configured OSPF on R1. What will happen? R1 will send hello message on this interface. The first message. It will send hello message and it will change the neighboring state to int. That it has initialized the hello packets. It has sent the hello packets. R2 will receive as soon as you configure hello packet on R2. Right now, is there any two-way communication? No. Okay. So what will happen? R2 will also send what? Hello packet. Okay. Now what will happen? The hello has been sent also, received also. So the state will change to two-way because two-way communication is there. Packets are getting sent also and received also. Okay. So the state will change to two-way. Now, once the state has been changed to two-way, they will, the router 1 and router 2, they will come to know that, okay, someone is there on the either side. R1 will come to know, okay, R2 is there. R2 will come to know R1 is there. Okay. Now what will happen? They will make an election for DR and BDR. Again, right now, just leave this concept for DR and BDR. Okay. Now, once they have the two-way communication, means they know that, okay, I have a neighbor. They already know that I have a neighbor. Now, next, what they want to do, they want to share the information. Okay. They want to share the information, but they have to decide that who will start sending the information first. First, R1 will send or R2 will send. Okay. So what they will do? They will send the next message, database description. These database description messages, these are used to exchange the database information. Okay. Like R1 will tell that, okay, I know these networks. R2 will say, I know these networks. They will share the information. They will share their knowledge. Okay. But what they will do, they want to decide that who will share first, who will start sharing the information first. So they will send empty database packets. They will send these packets, but in these packets, they will not send any information. Okay. Similarly, R2 will also send empty database, right? So by sending these databases, they are sharing the information about their router ID. They are sharing the information about router ID. Now, what is router ID first of all? Router ID is what? Identity. Okay. So router ID is similar to your IP address, 32-bit. Okay. Router ID is an identity by which your routers are identified in the OSPF. In your OSPF, all the routers, they are identified with their router ID. In OSPF, all the routers, they are identified with their router ID. But how do the router come to know about their router ID? So there are certain criteria for router ID election. The first criteria is manually configured. If you manually tell the router that use this router ID. First priority is given to the manually configured if you manually configure router ID on the router. Second priority, if no manually configured, if you haven't configured manually, that is what we do in the by default case, right? So what it will do, it will check highest IP on any loopback interface. Highest IP on any loopback interface. Okay, it will check the highest IP of the loopback interface and then it will take it as a router ID. If loopback also not configured, in that case, it will take up the highest IP of any physical interface. Highest IP on any physical interface. These are the criteria for router ID election. Okay. First priority is given to the manually configured. If you haven't configured manually, the router will automatically check for the highest IP on the loopback interface. If you haven't configured loopback also, in that case, the router ID will be the highest IP on any physical interface. So let's say here, if I have configured, for example, 10.0.0.1, and here I have configured 10.0.0.2. Okay. Now I will not configure manually on the routers. I haven't configured any loopback. So what will be the router ID here? This IP itself, 10.0.0.1 and 10.0.0.2. So when they are sending these empty database packets, they are exchanging this information about the router ID. Okay. Now, how they will decide whether who is going to send first? So they will do an election that is known as master and slave election. They will perform an election that is master and slave election. Who will become the master? The router with the highest router ID. So here, if you see, who will become the master? R2 will become. R2 is having a higher router ID, right? So right now they are just trying to exchange. They are preparing to exchange the database. So this state, when they are exchanging empty databases, this state will change to exstart. This state will become exstart, means they are preparing to start the exchange. Now, once your master and slave has been elected, so always your master will start the database exchange first, means he is going to send the database first. He is going to send the database description packet first, and in this database description packet, your master router is going to share the information. Okay. Similarly, this R1, first of all, OSPF is a reliable protocol, so it will send an acknowledgement. Okay. And this acknowledgement, in case of OSPF, it will be known as link state acknowledgement. So it will be known as LSAC. Okay. It will send an acknowledgement that, okay, I received your database, as well as it will also send its own database. Okay, so now what they are doing, exchanging the database. So this state will become exchange when they are actually exchanging the database, right? Now R2 received information from R1 and R1 received information from R2. Let's say R2 shared the information about the 10 network, 20 network, and 30 network. Okay, and let's say we have another network here, 1. So they exchange this information that R1 will say, I know about the 1 network and 10 network. Okay, 10 is already being used. Let's say 40. Okay, and R2 will say, okay, I know about 10, 20, 30, and 40. Now what your R1 will do, R1 will not have information about these networks. So R1 will try to ask more information that, okay, I do not know about these networks. How do I reach these networks? Right? R2 gave the information to R1 through the database. Now in the database, R1 doesn't know about some information, an information about a particular network, that how to reach that particular network. Okay. So what your R1 is going to do, it is going to ask your R2 for more information, that I want more information so that I can create a route. Okay. So for that purpose, it will be sending what? Link state request. So it will send what? Link state request, or in short, LSR. Okay, it will send a LSR asking for more information about a particular network or a particular route. Then R2 is going to respond to this request. So it is going to respond using the LSU, link state update. It will tell the, see, whatever information is required by your R1, that information it will provide using LSU. Okay, so now what they are doing, they are trying to complete the information. They are trying to get the missing information. So this state will be loading. Okay, and when they have all the information about each other, let's say R1 asked about all the information about R2 networks, R2 asked all the information about R1 networks, and now they know about all the networks. Both R1 and R2 know what all the networks are there and how to reach them. So they are fully synchronized. So the final state is what? Full. The final state is full. The full state means the router databases are fully synchronized. The router databases are fully synchronized. R1 knows about all the networks of R2. R2 knows about all the networks of R1. Okay. So this is how the states are changed. So the first state is what? Down. When your database is down, means when you haven't configured OSPF. In that case, the neighborship state will be down. Then when the hello packets has been sent, the state will change to init. Okay. And when the hello packets has been sent and received, the state will change to two-way. And at the two-way state only, the DR and BDR election happens. Okay. At the two-way state only, the DR and BDR election happens. So how a DR and BDR is elected? So election criteria you can check here. First of all, highest priority is checked for DR and BDR election, or let me say DR election criteria. Okay. First of all, highest priority will be checked. And by default, this priority will be 1. By default, OSPF priority is 1. So first of all, it will check for highest priority. Second thing, if the priority is equal, which will be equal in the by default case, all the routers will be having a equal priority. Okay. In that case, it will check for highest router ID. Okay. First of all, highest priority will be checked. If priority is equal, in that case, highest router ID will be checked. And how router ID is selected, that we have already seen. Manually configured, loopback, and if no loopback, highest physical interface ID. This is clear. Okay. So neighborship states and OSPF packets clear. Then we have router ID election. So first preference will be given to manual. Second preference will be given to highest loopback interface. Third preference will be given to physical interface IP, highest physical interface IP. DR election. First of all, highest priority. And if priority is equal, highest router ID. Okay. DR is what? DR is a designated router. DR is known as designated router. Now, let's say if your designated router goes down, so we need a backup also. So that's why we have your BDR, that is your backup designated router. Okay. So if this is having highest priority, this will have second highest priority. If this is having highest router ID, it will have second highest router ID. Same criteria. Okay. And what is the by default priority in case of OSPF? 1. This is clear? Okay.
Sounds clear.
Hmm.
The diagram.
Yes. I don't think it will go that bad. Okay, let me just try. Okay, no more backs. Yes, tell me.
That exchange with the database is getting.
Yes, see, in the exchange state, the database is getting exchanged.
That one you mentioned like from this side R2 to R1.
That is just a
Yeah, I got like validity based on IP.
based on router ID. So R2 will be master because R2 is having highest router ID. So master will always send the database first.
Yeah, 10.0.02.
Yes, 10.0.0.2.
That is highest.
That is highest.
Oh.
Okay. Usually, see what will happen. Your slave cannot send the database. Your slave cannot send the database. Only it can respond to the master. So if master is sending database, slave will just respond to that. Okay. But these things again part of your CCNP there you will study that your slave cannot initiate the database exchange. And if let's say master has done sending the database, then what your slave will do? Slave cannot send. And if slave has still more information, in the response, it will mention that, okay, I have more information. Then master will keep on sending empty databases and slave will respond to that. Okay. Now we'll see how DR and BDR is working and where DR and BDR concept is used. Okay, before that, like we discussed, in your OSPF 3 tables are created, right? The first one is neighbor table. So if you want to check the neighbor table, the command will be show IP OSPF neighbor. Okay, show IP OSPF neighbor. Then second table is OSPF database, or also known as topology table. To check that, the command will be show OSPF database. And if you want to check the routing table, how do we check the routing table? Show IP route. That will show you about all the routing protocols. Specifically, if you want to check OSPF, show IP route OSPF. If you want to check AGRP, show IP route AGRP. If you want to check RIP, show IP route RIP, show IP route static. Okay, like that. These are the commands. This is clear? Okay. Now, how do your tables look like? Check. And if you want to check what all the protocols are running on a router, what is the routing protocol that is running on the router? Okay, that also you can check. Let's say this is R1. I want to check that which routing protocol is running. So you can give show IP protocols. This is the command. And it will tell you the routing protocol is what? OSPF. Okay. Then what is the router ID? What is the number of areas configured? Okay. There are different types of areas that you'll study in your CCNP, that there is normal area, stub area, not so stub area. Okay. Then for which networks it is performing the routing. Okay, and what are the routing information sources? So why this IP is here having 3112? This is the router ID for your second router, R2. Because if you see on the R2, first of all, manually configured, we did not manually configure. Second priority is given to highest loopback IP, and it is having the loopback interfaces. And in the loopback interfaces, what will be the highest IP? 3112. So that's why it is showing this IP. And for R1, what will be the router ID? 12.1. Okay. So that's why it is saying that from where the information is coming, the information is coming from 12.1, that is self, and the second is 3112, that is your R2. Okay. So first of all, let's check the neighbor table. Show IP OSPF neighbor. Okay. So tell me, who will become the DR between R1 and R2? See, what will be the router ID here? 192.168.12.1. Here router ID will be 30.1.1.2. Now let's come to the criteria of election. First is highest priority for DR election. Correct. Priority by default 1, by default 1. Okay. Second, highest router ID. Now who is having the highest router ID? R2 or R1? 30.112, 192.168. Who is higher? Obviously 192, right? So this will become what? DR. And R2 will become BDR. Okay. This is clear. Because obviously 192 is far higher than 30. Okay. So let's check. So on R1, if I'll check, R1's neighbor will be R2 and it will be showing as BDR. What is the router ID? 3112. What is the by default priority? What is the neighborship state? Full. Full means fully synchronized. Then what is the role? BDR. Okay. What is the actual IP? 12.2. On which interface? G0 by 0. This is clear. Okay. Similarly, if I will check on R2, it will show R1 as DR. Show IP OSPF neighbor. Neighbor ID, this is the router ID, priority, full, DR, IP address, and on which interface? Gig0 slice. Okay. Then second thing, the topology table or the database. Show IP OSPF database. Okay, so this is how the database looks like. Okay, we will understand this database, but this is how you check. Okay. Then third is routing table, show IP route. If you want to check specifically OSPF, then only OSPF, and it will show you only and only OSPF routes. Will not show you connected and other routes, because specifically you can check for only OSPF. And these are the routes learned via OSPF. Okay. Then one more thing you can note down here. In case of OSPF, see, your RIP uses, yes, Vincent.
Actually, in DRB, they are no,
Mhm.
but router ID is the highest priority. Have to take which is a PDR, right?
First priority will be given to, first preference will be given to the highest priority. If the priority is a type, because by default R1 is having the priority 1, R2 is having the priority 1.
Okay.
Priority is a type, in that case, highest router ID it will check.
But in R2, there is a router ID is there, no, sir? 192.168.12.2.
No. That is not the router ID. Router ID is 30.112.
But you take in R1 as a 192.168 as a router ID.
Yes, 12.1 is the router ID, because there is no manual configuration, no loopback interface. So only one IP is there.
Okay.
Okay.
Suppose that loopbacks are all not there, 12.2 would be there.
Only if these two IPs are there.
Ah,
In that case, obviously, this will become the DR, because it will have higher router ID 12.2, and this will have 12.1. Okay, if the loopbacks are not there, in that case, this will be the DR.
at that point it should match.
Yes. Yes, one more thing you should note down here, that your RIP uses the metric what? Hop count. Right? Your EIGRP uses the metric what? K values. And these K values are what? K1, K2, K3, K4, and K5. That is bandwidth, load, delay, reliability, and MTU. Correct? Your OSPF uses the metric as cost. Uses which metric? Cost. Now, how the cost metric is calculated? So there is a formula, cost equals to reference bandwidth upon interface bandwidth. Reference bandwidth upon interface bandwidth. And where the reference bandwidth is fixed. Reference bandwidth equals to 100 Mbps. The reference bandwidth is what? 100 Mbps. Okay. So that means your ultimate formula will be cost equals to, let's say, 100 upon whatever interface bandwidth is there in the Mbps. Okay, this should be in the Mbps. And you will get the cost. For example, let's say you have 1 Gbp link, 1 Gbps link. So that means your cost will be like something like cost equals to 100 upon, like 1 Gbps, consider 1000. So this will be 0.1, but it will be considered as integer as 1 only. Is that clear? If less than 0, that will be 1. Okay. If you are having, let's say, for example, 10 Mbps link, then cost will be 10. Okay. This is clear? All right.